Guys, welcome back to TechDose, and in this video we will look at Domino and Tromino tiling problem, which is from Leetcode number 790. We will be looking at two approaches in detail. The first one is going to be recursion with memoization dynamic programming, and the second approach will be going to be dynamic programming with the tabulation, and along with that the proof of formulation will also be shown. Let's now read the problem statement. In this problem you have two type of tiles, a 2 by 1 domino shape and a Tromino shape. You may rotate these shapes in whatever way you want. So this is the domino tile, and the Tromino tile will have 3 cells. Now if you consider this Tromino tile, if you rotate it in one way you can get an inverted format. Another way could be like a reverse L, and you can have a L shape, right? Given an integer n, return the number of ways to tile a 2 by n board. Since the answer may be very large, we have to return modulo 10 to the power 9 plus 7. In a tiling, every square must be covered by a tile. Two tilings are different if and only if there are two 4 directionally adjacent cells on the board, such that exactly one of the tilings has both the squares occupied by a tile. Now if you look at the given example, then in this case we are given n equals to 3. That means we have actually 3 number of columns, and you can say we will always be having 2 number of rows, because this is a 2 by n type of board. So the number of rows is going to be same, R1, R2. Now in this case, if I just mark the column numbers 1, 2, 3, then in how many ways can you fill up all the tiles, provided you have a 2 size domino and a 3 size Tromino, right? So you can just use these two shapes in any way you want. So one way could be just make this domino straight, that means vertical, and then you can connect these two horizontally, right? That is one way, and that is shown here in the first configuration. Another way could be to connect all of them vertically, and this has been shown in the second example. The third example here shows that first 2 points are joined horizontally, and then the last one is joined vertically, right? This one is showing a L-lock hook. Okay, so this is one way which is shown in the fourth example, and in the fifth example it is showing a different way to create the L-shape hook, right? So I think this is clear. You do not have more than 5 ways. Therefore the result in this case for n equals to 3 is 5, right? Now when you have n equals to 1, then you just have this one column, and there is only one way where you can connect them vertically, right? And that is why the answer is 1. Now in this entire problem, the n value is 10 to the power of 3. So in any case, whatever complexity you write, you should make sure that the number of computations are less than 10 to the power 8 for it to pass. So if you write, let's say, an n square algorithm, then n square will be 10 to the power of 6, and it is less than 10 to the power of 8. So this is also going to pass within 1 second, right? Now having understood the entire problem, let's now look at the possible tile shapes that we can have. So here we are taking an example with n equals to 5, and you can see that I have 2 rows and 5 columns. Now in how many ways can we actually mark the tiles using the domino and the Tromino? So you look at it that we have actually 6 possible shapes that we can use. So using the domino I can make only 2 shapes, either horizontal shape or vertical shape. But using the Tromino I can make an L hook, I can make an inverted L hook, and also for this L I can mirror it and create a reverse L, and for this inverted L I can make a mirror of the inverted L, right? So these all shapes will actually be used in order to mark all the tiles, in order to fill all the tiles using the domino and Tromino. So in this case I will be solving by moving from right to left. Well, you can also solve by moving from left to right, but your stopping condition will always be the value n, right? But if you move from right to left, your stopping condition will always be 0, which is out of bound on one side, right? So whatever is the value of n, if you move from right to left, you know 0 is the stopping point, so you don't have to remember what was n. But if you move from left to right, then you have to always keep track of n, whether you have reached to n or not, and you have to also remember the value n, right? So in most of the dynamic programming problems, I personally prefer to move from right to left, from a higher to a lower index. Okay, that is my reason for moving from right to left. The goal here is to fill all the cells moving from right to left. I think this is clear. Okay, now if let's say I put horizontal lines being present at 5. Let's say my R1 was present at 5 and R2 was present at 5, where R1 and R2 are, let's say, 2 pointers which will be indicating at what cells I am looking at which is not filled, moving from right to left, and as we sweep the line from right to left, then I will make sure that everything to the right hand side of R1 and R2 are all marked. Otherwise, if any of the cell is not marked, I will not move these pointers to the left hand side. That is what I will be assuming. So initially R1 and R2 will be starting at index 5. If I put horizontal line between this 4 and 5, then is it a valid line? Yes, definitely it is valid. So at which index I will end up with? So R1 will move from the index 5 to index 3 because everything to the right of 3 has now been marked. So I will be moving from R1 to R1 minus 2, and the same goes for R2. It will be moving from R2 to R2 minus 2, and that will be the index update if you try to end the horizontal line at index R1 and R2. Okay, I think this point is clear. Now what if I had not put the horizontal lines, but instead I would have put the vertical lines? Then what would have happened? If you put one vertical line, yes, it is valid, then I will be moving from R1 to R1 minus 1 and R2 to R2 minus 1, right? That would be my update. So you look from R1 to R1 minus 1 and from R2 to R2 minus 1. So this is how the index will be updated, moving from right to left when we put either the domino or the tromino. So this is the case for domino. What about the case for tromino? Like in this case, we cannot put all different kind of shapes. We have to just check the condition. In this particular case, I can put a mirror L shape. That means you can say a reverse L shape, right? If I put something like this, will it be valid? Yes. So the R1 will move to R1 minus 1 and the R2 will move to R2 minus 2. You see this case? R1 is moving from R1 to R1 minus 1 and R2 is moving from R2 to R2 minus 2. Okay, I think this case is clear. Now, can I put a different type of L structure, something like this? Yes, this is possible, and R1 will move to R1 to R1 minus 2, R2 will move from R2 to R2 minus 1. So you see this case, R1 to R1 minus 2, R2 to R2 minus 1. Okay. Now, can I put a L shape here, like something like this? Well, this is not possible, because for an L to be present, actually this R1 should have been present at this point 4, and everything to the right must have already been marked in such a way that I will mark all these 3 cells. But when R1 is equals to R2, then this case will not hit. Okay, this case will not hit. And can I put something like this? Well, something like this will be possible if R2 was present here at R1 minus 1 in such a way that I can mark these 3 cells and this was already marked. In that case only this inverted L will be used, otherwise it will not be used. So whenever R1 equals to R2, you can see that I have 4 cases. The horizontal line, vertical line, that means the domino will always be used here, can be used, and the mirror of the L and the inverted L can be used here. So these are the 4 things that can be used. So all 4 cases have to be tried, and these are the 4 cases. Out of 6, we have to use the 4 cases. Now let's consider a case that shows you had actually marked something like this. Okay, let's say you had marked something like this, and your R1 and R2 are given in this way. Okay, R1 is pointing to 3, R2 is pointing to this 4. Then what kind of structure can you put now? Well, one thing that you can do is you can put horizontal line. But can we put horizontal line between 2 and 3? Yes, it will seem like you can put horizontal line between 2 and 3, but what we will suggest is we will always be trying to balance R1 minus R2. Absolute should be less than equals to 1, so that I will be sweeping R1 and R2 together from right to left, and the difference between the indices will never grow beyond 1. You can follow this kind of strategy, okay, to optimize your time complexity. Fine. If you don't optimize it, still it will work, but the time complexity will not be optimized, and hence you will find more runtime and amortized time too. So in this case, I will try to follow that R1 minus R2 absolute is less than equals to 1. So if I have to put horizontal line, then I will not put it at 3, because 3 is less than 4. So I will put a horizontal line here, and move R2 to R2 minus 2, and R1 will remain at the same place, isn't it? R1 will remain at the same place. That is what I will be doing. And what else can we do? We can do an L shape here, and if I do an L shape, then R1 will be moving from R1 to R1 minus 1, R2 will be moving from R2 to R2 minus 2. Okay, so I think you are clear with the two cases which will happen when R1 is less than R2. But what if I say that I had used this kind of structure, a mirror L, and R1 is here and R2 is at this point, where I say R1 is greater than R2. So for this case, if I have to put a horizontal line, yes, I can put it, but I can put only for R1 and move R1 to R1 minus 2, so that the difference between R1 R2 is never below 0 or never beyond 1, you can say, right? Which is the absolute value. Okay, or I can also use this kind of structure and move R1 from 4 to 2 and move R2 to 2 as well. Okay, so these are the only two tiles that I can use in such case. So there are three cases, right? In the first case, when R1 and R2 are equal, I will be using four cases: horizontal, vertical, and these two structures. When R1 is greater than R2, as you see here, R1 is greater than R2, then I will be using the horizontal on R1 and update this R1 only and keep the R2 at the same place. Or I will use the inverted L hook, something like this, and update the R1 to R1 minus 2 and R2 to R2 minus 1. Okay. Otherwise, in the third case, when R1 is less than R2, that means if R1 was here, then I can do only a horizontal on R2 and move R2 to R2 minus 2. That is one thing. Or I can use an L shape and move R2 to R2 minus 2, R1 to R1 minus 1. So you see, these are the only two things that are added. So I think all the cases are clear about how we will be sweeping our two pointers R1 and R2, and always make sure that R1 minus R2 mod, that means absolute, is less than equals to 1. Okay. So I hope you have understood what we are trying to do. So I have already mentioned all these points here. If R1 equals to R2, I will be using horizontal, vertical, and these two trominos. R1 greater than R2, these two structures, and R1 less than R2, these two structures, right? So let me show you a recursion tree diagram flow, which will help you visualize the entire problem. So in this case, I am taking an example for n equals to 4, and I will be moving R1 and R2 from 4 and moving from right to left. So any node here is showing R1 comma R2 index. So when we are at 4 comma 4, then we are hitting case number 1, from where I can put a vertical line and move both of them to the left hand side, or put horizontal line and move both of them to the left side, or put an L structure like this, or put another L structure, something similar to this, right? The two Tromino structures. So in any case, if you put horizontal line, something like this, then you will be moving to 2 comma 2. Okay, so you see that from 4 comma 4, I will move to 2 comma 2. If you had put a vertical line, you will move to 3 comma 3. If you put a L structure, something like this, then you will be moving from 4 to 2, and the R2 will move from 4 to 3. Okay, so you see, you will be moving to 2 comma 3. And another type of structure that you can use is this, where you will be moving to 3 comma 2. Okay, so you see, I have moved to 3 comma 2. So these are the four options when R1 equals to R2. Similarly, for 2 comma 2, I will be updating to 0 comma 0, 1 comma 1, 0 comma 1, 1 comma 0. You know that 0 is out of bound here. So if any of the R1 or R2 is going out of bound, then I can simply return 0. That means it is impossible to get a valid tiling, because if you were tiling something like this, okay, and then you suddenly use an L structure here, then this endpoint is outside, and so it is not a valid arrangement. Fine. But if both of R1 and R2 together are moving to this point, that means everything to the right have been properly tiled, and that is why R1 and R2 has moved together to the 0 point, right? And this is valid. So whenever you hit 0 comma 0, we have to return a value 1 for the count. If you solve for this 1 comma 1, you will see these out of bound cases, and this 0 comma 0 will be the only one which returns a value 1. Okay. Now these all are the states. You can say these are all our sub problems. The sub problem, because if you consider this entire portion as the actual problem, the actual problem is solve for 4 comma 4, and tell me in how many ways can I tile an entire 2 by n matrix in such a way that my both the pointers r1 and r2 are at 4 comma 4. So if I put an L structure here, something like this, then the sub problem will be 3 comma 2. So tell me in how many ways can I tile 3 comma 2, and to that I will be multiplying by one way, because these three points can be covered in one way, right? Something like that. If you had covered these 2 points in, let's say this is one way and this is another way. Let's say we have 2 ways to cover these 2 points. So if there are 2 ways, then tell me in how many ways can I cover these points. And if I cover these points in, let's say 2 ways, then to these 2 ways I will be multiplying it by 2 other ways and get 4 ways. Okay. So the entire problem is 4 comma 4 that I want to solve, and all the nodes that you see internally are the internal subproblems. So in order to optimize this recursion, I will be saving the subproblem result in a table called memoization table, which will be of size n by n in such a way that your state can be anything, like r1 value can range from anything from 0 to n, and r2 value can also range from 0 to n. So if you consider all possible subproblems, it will be the cross product. That means for 0 you can have 0, 1, 2, 3 and so on till n, and for 1 you will have all these combinations as well. So you will have n square such combinations, right? So I'll be making a table of size n square n by n. Whenever I get a value, then I will be saving it. Now 0 comma 0 is a base case, so I will just be writing in the recursion code as base case. For 1 comma 1 I will save a value 1 because I got a count of 1. Okay, and this will be returning a value 1 as well. Now for 2 comma 2, this will be trying to get a Tromino shape, something like this, and so I will be moving to 0 comma 1, which is invalid, and so this will be returning a value 0, and this will also be returning a value 0. So what was the answer at 2 comma 2? 1 plus 1 plus 0 plus 0, which is 2. So at 2 comma 2 you can save the answer as 2 and return the value 2. If you go to this 4 comma 4 again, you have tried all the combinations starting with the horizontal lines. Now you can start with the vertical line. If you do that, then you go to 3 comma 3, and again at 3 comma 3 you try out all the 4 possibilities one by one, and you will end up with, let's say, 1 comma 1. 1 comma 1 is a repeating sub problem, right? So you can simply look at it. Okay, it is already calculated. You look at it and just return the value. Return the value as 1. If you look at 2 comma 2, this is also repeating because it has already been saved. So return the value as 2. If you look at 1 comma 2, this is not saved. How do we know it is not saved? In the memoization table, you can save -1 values or anything which will not be in the possible count range. Negative values will not be in the count range. So you can fill it with any negative value. I'll be filling with -1. And you can say that memoization at 1 comma 2 is -1. So it is not calculated. I have to calculate it. If you try calculating at 1 comma 2, then this is the sub problem that we are trying to solve. In how many ways can we do that? So if you apply the horizontal on R2, then the R2 will move to 0, the R1 will still remain at 1. Okay, so this is invalid. So return 0. If you try an L shape here at 1 comma 2, then both R1 and R2 will move to 0. This is valid, so return 1. So this gets a value 1. So at 1 comma 2 you can save 1 for future reference, and this will be returning a value 1. Okay. Now it is making a call to 2 comma 1 because at 3 comma 3 I am trying to make this L shape. So I will be going to 2 comma 1. Has it been calculated? No, it has not been calculated. I'll try to calculate it. So for 2 comma 1 I'll try to put a horizontal line on the first row because R1 is greater than R2, and I will move to 0 comma 1, which is invalid, return 0. If I put something like this, then I'll go to 0. Both the pointers will go to 0. So I have done a proper tiling. Therefore this will return 1. So 2 comma 1 will have answer 1. You can save it here, and this will be returning a value 1. So what did 3 comma 3 get? 1 plus 2 3 plus 1 4 plus 1 5. So this got 5. So at 3 comma 3 you can save 5, and this is returning a value 5, right? On the side 2 comma 3, how did we get it? You put an L structure here, the Tromino. So you go to 2 comma 3. Okay. So if you go there, then has it been already calculated? No. So let's try to calculate it. Now at 2 comma 3, if you have to apply horizontal line, where will you apply? In the second row. So you will move to 2 comma 1. Okay. So I have moved to 2 comma 1. If you look at it, it is already calculated, return the value 1. It is repeating sub problem. If you try to put an L shape here, okay, at 2 comma 3, if you put an L shape, it will be something like this. So you move to 1 comma 1. 1 comma 1 is already calculated to have value 1, so this will return 1. So this got a value 2 and it will be returned. Now another shape at 4 comma 4 which can be applied is an L shape, the mirror L shape. So you will go to 3 comma 2. So let's go to 3 comma 2. At 3 comma 2, if you have to apply horizontal line, we will be applying at R1 because R1 is greater than R2, right? So I'll be going to 1 comma 2. Has it been calculated? Yes. You can return a value 1 from here. Now you can also apply this Tromino shape, inverted L, and so I will be going to 1 comma 1, which is already calculated to have value 1. You can return 1. So this will be getting value 2, 1 plus 1. This will return 2. Okay. So what does this problem 4 comma 4 get? It is getting 2 as a count when you start with the horizontal lines. It is getting 5 as a count if you start with a vertical line. It is getting 2 as a count if you start with an inverted L shape, and another type of inverted L shape if you start, then you get 2 count. So the total count that you get is 5 plus 2 7 plus 2 9 plus 2 11, and therefore the result in this case is going to be 11. There are 11 ways to tile when n is equals to 4 and you have the given domino and tromino, and you are allowed to change the shapes as you wish, right? So for 4 comma 4 I'll be saving 11 here, and this will be my result. The result will always be n by n, which is this last cell. I think this is clear. Now in this case, if you consider the space complexity, it is going to be order of n square, right? But if you consider the time complexity, it will be order of n. Even though it looks n square, it is order of n. And why is that? Because we are sweeping both the points R1 and R2 from the right hand side, maintaining that the difference between R1 and R2 is never exceeding the value 1. Okay? Because whenever, let's say, R1 was at certain point here and R2 was at certain point, then I have written the cases in such a way that if R1 is greater than R2, then if I have to put a horizontal line, I'll always put it here. I will never put at this point, okay? So that R1 do not fall back by a distance more than 1. And how much imbalance can happen, like the difference in gap? It will always be maximum 1 if I follow this strategy in 3 cases, because an L shape will only increase the difference by 1. Okay, so as soon as R1 and R2 are not equal, then I will be adjusting how we actually tile by using these 3 cases. So if you use these combinations, then you can always maintain that you will be solving this in order of n time, and because this R1 R2 difference, absolute difference, will always be less than equals to 1. If you do not follow this, if you try all combinations, it is going to be order of n square. Okay, so I have actually optimized it by using this strategy, so it is order of n. I hope it is clear, right? Now let's look at the code for this approach 1. If you are someone who is looking to prepare for top product based company within a limited time of just 3 months, then we have brought for you both the DSA and the system design live interview training program. The most important feature of this program is you get a filtered and condensed structured curriculum, in-depth discussion of all the topics, and my guarantee of your understanding, one-on-one guidance with me, and live weekend classes. To know more about the training, you can WhatsApp us on this given number. In this problem, we are given the n value, and I am calling the count tiling ways by passing the R1 and R2 pointer. So I'll be parsing from right to left, so I'm passing n comma n. Now if you look at the base cases, if R1 and R2 are both 0, then I'll be returning 1, which is a valid tiling. Okay, the tiling has been done. If R1 is less than equals to 0 or R2 less than equals to 0, then the tiling is invalid because something is left on the right hand side. Okay, if the sub problem is already calculated, return it without having to calculate it again. Otherwise, count the number of ways from the given sub problem at any position R1 and R2, right? Find this sub problem, the number of ways to tile this entire sub problem. Okay, so this is the first case where R1 equals to R2, and I told you that I can do horizontal marking, the vertical marking, the inverted L shape, right? If R1 R2 are same, inverted L shape something like this, the mirror L shape something like this, right? These all 4 cases will be there when R1 equals to R2. When R1 is greater than R2, R1 is greater than R2, then if I have to put a horizontal line, it will be for R1. So the horizontal tile will be only for row 1, and I can put something like this, the inverted L shape, right? So these are the two cases. Otherwise, when R1 is less than R2, then in this case, if I have to put a horizontal line, it will be for R2. Okay, so the horizontal tile will be for R2, and if I have to put a Tromino, then it will be like a L shape. Okay, so these are the three cases, and if you follow this, then you will maintain the time complexity order of n. And before returning, we have to always save it in the memoization table, and as mentioned in the problem, we have to always take mod of 10 to the power 9 plus 7, right? So this is approach number 1, and I hope it is clear. Let's now look at the tabulation approach. Let's look at the sub-problems incrementally in order to get an understanding for the tabulation approach. Now in this case, the smallest value of n is going to be 1, because n's range is from 1 to 1000. Okay. Now if you just have one column, you will always have two rows. If you have one column only, then there is only one way to tile it up, by using a vertical line which is representing, and I will always be representing dp at I with the number of ways to tile for n equals to I. Okay, so if you have I columns, that means I columns and definitely two rows, then what are the total number of ways to tile will be stored in dp at I. Okay, so dp at 1 will be storing 1. If you have one column, means you have only one way to tile it up. Now similarly, if you have two columns, then what happens? You can put two slashes here, like two vertical lines, and this is one way by using two dominoes, vertical dominoes, and you can put horizontal dominoes, and this will be another way. So there are two ways, and therefore dp at 2 equals to 2. But what happens actually is, when you put a straight line, that means a vertical line, then I will be calculating the total number of ways to tile for the sub problem n equals to 1, and to that I will be multiplying this one way, because this is one way to do it, right? So in this case, this is the problem which we have already solved, which is dp at 1, and there is exactly one way to tile for n equals to 1. So I'll get this 1 and multiply with 1 and get a value 1. So this will contribute to a value 1, and I will represent it as this one as dp at 1 and a vertical line, saying that I have put a vertical line for n equals to 2 and then reduce the sub problem to dp at 1. Okay, and this is how it is represented. For the horizontal lines, if you put two horizontal lines here, then the sub problem will be going to dp at 0, because two columns have been used. So if n value was 2, it will go to n value 0. So what should be the count here? Count should be 0, right? So 0 multiplied by 1 will come out to be 0, but this is one way. So just to maintain identity of multiplication, I will be assuming that the 0 size subproblem will have one count. Actually, it should have 0 count, but this problem will not occur because n will always be asked from 1 to 1000. So to maintain the identity of multiplication, so that the way count do not go to 0, I'll be maintaining dp at 0 to be 1. So if I do that, 1 into 1 is going to be 1, and this will be represented as dp at 0 and two horizontal lines. Okay, so you add this up and this will be 2. Similarly, now you can understand what will happen if you put a vertical line here. It will be converting to dp at 2 and a vertical line. You see this? And dp at 2 is two ways, right? And a vertical line is only in one way. If you put horizontal lines here, then this will be giving you dp at 1 and two horizontal lines, right? dp at 1, two horizontal lines. And if you put L-shape hook here, something like this, L-shape hook, then this will be equals to dp at 0 and L-shape hook, right? Because you have used up 3 columns. So where will you go to the left hand side? It will be the sub problem starting from 0, right? So that is why it is dp at 0 L hook. And if you try another type of L hook, something like this, then still you will be going to dp at 0. So dp at 0 and a different configuration of L hook. So this is one way. This is one way to do, because dp at 0 is 1 and this is one way, right? And this is one way. So total ways are 5 here. If you go for a higher n value with 4, then you will see if you put a vertical line, it will be dp at 3 and vertical line. dp at 3 is 5. So this will be 5 ways. Now if you put two horizontal lines here, then you will go to dp at 2. This will be the sub problem, dp at 2 and two horizontal line, dp at 2 is 2. So this is 2 ways. Now if you put the L hook something like this, then this will be dp at 1 and multiplied by one way. So this is one way simply, right? dp at 1 is 1. So this is one way, and dp at 1, and this another type of L hook. This will give you one way. Now there is another configuration here with an L starting with a horizontal line and a reverse L. This is one way, and if you use this, will be using 4 columns altogether. And similarly, if you try in another way around, like what if you had tried something like this? Okay, then this will be giving you another configuration, and this is also consuming all the 4 columns. So this is another way, one way. So total ways are 11 here, right? So I think now you are able to understand what we are trying to do. If you try and calculate for n equals to 5 with that same approach, then I think for the vertical line, horizontal line, the simple L hooks you can do it, and this one also is similar because this is consuming 4 columns altogether. If you remember, an L here, a slash, and another L, right? This is this one. So I will be going to sub problem starting with 1. Now there is another type of problem in this case. You see this structure. This is an L with a slash, another slash, and ending with an L. So it is kind of L will bracketize, and in between you can have any number of horizontal line which is just not aligned by one position. Okay, you can say something like that, and this pattern can infinitely go. It can infinitely go, and at the end it will be actually closed by another inverted L shape, right? It is not just confined to this 5 columns. Okay, it can go next time to 7, 8, or 9 columns as well. So you check it out. So if you add up all these cases, it is going to be 24. For n equals to 6, again you can go through this entire thing. You see how it is increasing, right? So all these horizontal lines can go infinitely. It can go infinitely. It depends on what is your n value, and at the end it will be just closed by your bracketization simply. Okay, so both these cases have different type of closing brackets, and so different configuration. So if you add up all these cases, you will always find that the number of ways in this particular case is dp at 5 plus 4 plus 2 times of dp at 2, dp at 1, dp at 0. You see that these 2 times are repeating from this 3. It is 3, 3. This will be 2, 2. This is 1, 1, 0, 0, and so on. Okay, only the first 2 terms here are not occurring 2 times. And this will always be true for whatever sub-problem you solve. You try it with n equals to 7. You will see that the 6 and 5 are the ones which will be occurring exactly 1 time as it is occurring here. But the rest of them will be occurring 2 times. So 4, 4, 3, 3, and so on till 0, 0. Okay, so that is how this has been written. And you can also generalize this saying that dp at I equals dp at I minus 1 plus dp at I minus 2 plus 2 times summation k equals to I minus 3 to 0 or 0 to I minus 3 dp at k. Okay. So let's look at the generalized representation, a reduction of the formula. dp at n equals to dp at n minus 1, dp at n minus 2, and 2 times of all the rest of the solutions added together, right? So if you write it simply, you can just take out this dp at n minus 3. So it is 2 times. So I will club one time with dp at n minus 2, and one time I will keep it as separate. And now this entire thing will be reduced to 2 times of dp at n minus 4 to 0 because I have removed this n minus 3 outside. Okay. Now you know that dp at n minus 1 is n minus 2 n minus 3, and then 2 times from n minus 4 to 0. All this summed up together. Fine. So what I will do here is, if you see, I will be clubbing up this item with this item here. Okay, if you see this n minus 2 n minus 3, here it is n minus 2 n minus 3, and these all values from 2 times n minus 4 to 0. This is 2 times n minus 4 to 0. So this thing together is becoming dp at n minus 1, right? So I can replace these two with dp at n minus 1. So dp at n minus 1 is already present. So we get 2 times dp at n minus 1 plus dp at n minus 3. And that is how this formulation is derived from the given past example, saying that dp at n will be calculated to be equals to 2 times dp at n minus 1 plus dp at n minus 3. Okay, so these all simulations are important. You should go through these simulations yourself and make the diagrams, and then you can arrive at this result. And I hope you have understood how we have reached to the final derived representation, right? Now let's see a dry run. Once you know the representation, which is the most difficult part of this problem, then solving it is very straightforward. Let's solve for n equals to 5. Okay, so I will be taking a dp table of size 6 from 0 to 5, and dp at 0 will be 1. This is just for the identity. Okay, 1 is 1 and 2 is 2, because if you just have two size sub problem, there are only two ways: either you put vertical lines or you put horizontal lines. If you have only one size sub problem, you just have one way, which is a vertical line, right? Now for dp at 3 and beyond this, you can always fill it with the formula dp at n equals 2 times dp at n minus 1 plus dp at n minus 3. So if you calculate dp at 3, it will be equals to 2 times dp at 2 plus dp at n minus 3, which is dp at 0. So this will be equals to 4 plus 1, which will be 5. So fill this with 5. dp at 4 will be 2 times dp at n minus 1 plus n minus 3, which is 10 plus 1, 11. Similarly for 5, 2 times whatever is at 4, which is 22, plus 5 minus 3, which is 2. It is 2, right? So it will be equals to 24, and you fill it with 24. So I think tabulation is very simple, but you have to know how this reduction has occurred. Okay, so in this case the space complexity is order of n. Because of the dp table, it is a linear one, and the time complexity is going to be order of n as well. So this can be considered to be an optimized approach. Let's now look at the code. In this problem we are given the n value, and if n is less than 3, then I can simply return n, because those many ways will be present. The mod, which is 10 to the power 9 plus 7, the dp table of size n plus 1, which will save the values from 0 to n. dp at 0 is the identity value for empty board, which is 1, and 1 and 2 are 1 and 2 ways, right? So this is the formulation. This 1 ll is just to convert this number to 64-bit integer, so that the overflow do not happen before taking the mod. Okay, and after doing this, the final value will be our answer. This is the answer, dp at n, because we were trying to calculate if we have n columns, that means a 2 by n board, then in how many ways we can tile. And as I said, dp at I was saying if I have I number of columns, then in how many ways I can tile a 2 by I board. So that I value equals to n will be the final answer, right? So I hope we are clear, and if you still have any doubt, then feel free to comment below and I'll try to help you as soon as possible. See you guys in the next video. Thank you.